Welcome to BuildBytesDaily. Today, we're going to put on our detective hats and investigate one of TypeScript's most powerful but sometimes tricky features, type narrowing. If you've ever found yourself basically arguing with the compiler, trying to prove something that seems totally obvious, then this explainer is for you. We're going to crack the case on why TypeScript acts the way it does and learn exactly what clues it needs to see things our way. Let's dive in with our first mystery. Okay, so take a look at this. Our first mystery is a function called paddLeft. Seems simple enough, right? Its job is to add some padding to a string. That padding can be a number for spaces, or it could be a string that gets stuck on the front. But wait, what's this? TypeScript is throwing an error. It's complaining that a string or a number isn't a number. But why? The code looks like it should work just fine. Well, the root of the problem is this thing right here, a union type. That single vertical bar tells TypeScript that our padding variable has two possible identities. It could be a number, or it could be a string. And until we, the detectives, can prove which one it is in a given moment, TypeScript has to play it safe and assume it could be either one. It's really just trying to protect us from bugs later on. And here's where things get messy. The JavaScript.repeat method is, well, it's picky. It only works on numbers. You can't tell a string to repeat itself 5 times. That doesn't make sense. So TypeScript sees our padding variable with its dual identity and just throws its hands up. It says, whoa, hold on. I can't guarantee this is a number, so I'm not going to let you call a number-only method on it. This is where our detective work really begins. And the solution to this whole mystery has a name: narrowing. Seriously, think of it like this. You're a detective giving clues to the TypeScript compiler. Based on the evidence you provide, TypeScript can logically deduce or narrow down a variable's broad type, like string or number, into something way more specific, like just a number. But, and this is key, it only does this inside the block of code where your evidence is valid. And check this out. This is our first big clue in action. By adding a simple if statement that checks type of padding equals number, we've given TypeScript rock-solid proof. Inside this if block, TypeScript is now like, okay, I get it now. Padding is 100% a number in here. And poof, the error vanishes. This little check is called a type guard. It literally guards the code inside that block, making sure that the types are exactly what we expect. Now that we've cracked our first case, let's officially open up our detective's toolkit. These are the fundamental, everyday techniques you're going to use all the time to uncover the true nature of your types. So we'll be looking at 3 core methods. We've already met type of guards. Next, we'll investigate truthiness checking, which is a really quick but sometimes tricky way to filter out null values. And finally, we'll see how a simple equality check can be a surprisingly powerful tool for narrowing things down. But before we move on, a quick warning from an old case file. The type of operator has this famous historical quirk. Checking the type of null in JavaScript actually returns the string object. Yeah, it's a bug from way back in the day that was never fixed. TypeScript knows about this, of course, so when you check for an object, it knows it could be a real object or it could be null. It's a classic trap to watch out for. All right, next up is truthiness checking. You know how in JavaScript you can throw pretty much any value into an if statement? Well, some of those values, like null, undefined, an empty string, or the number 0, are considered falsy. They act just like false, so a simple if my var is a super fast way to narrow away all those falsy values. It's especially handy for getting rid of potential null or undefined errors. But, and this is a big but, here's a pro tip. While truthiness is fast, it can be a bit of a sledgehammer. Let's say you're writing a function that actually needs to do something with an empty string. A simple if my var check will just skip right over it because an empty string is falsy. So, always think twice about whether you might be filtering out valid data. Okay, this is where TypeScript gets really smart. Check this out. Here, x could be a string or a number, and y could be a string or a Boolean. Now, when we check if x equals y, TypeScript does some serious logical deduction. It figures that the only way this statement can possibly be true is if they share a common type, and the only type they both have in common is string. So boom, inside that if block, TypeScript knows for a fact that both x and y are strings. How cool is that? All right, we've mastered the basics. Now it's time to level up and look at some advanced sleuthing techniques. These are the tools you'll need when you're dealing with trickier cases, like complex objects and classes. First on our list is the in operator. This thing is perfect for when you have a union of different object shapes. So let's say a variable animal could be a fish or it could be a bird. By checking if in animal.swim, we're just asking, hey, does this object have a swim property on it?
If the answer is yes, well, TypeScript knows it's got to be a fish, and we can safely call animal.swim.
Next up is instanceof. This is kind of like in, but it works with classes and constructors. It basically checks an object's family tree. In this example, if our variable x is an instance of date, we know it was made from the date class, and we can safely call date-specific methods like toUtString. And if it's not, well, in the else block, it must be the only other option left, a string. So far, all our detective work has been reactive. We find a problem, and we fix it. But now we're going on the offensive. This is the master strategy: discriminated unions. This isn't just about solving type mysteries. It's about designing our code so cleverly that the mysteries can't even happen in the first place. So let's start with a really common mistake. Here we've got a single shape interface trying to describe both circles and squares at the same time. The radius is for circles, side length is for squares, so we make them both optional with that little question mark. But look, even if we check the shape's kind, TypeScript is still confused. It can't connect that check to whether radius is actually there. It still thinks radius is possibly undefined. So what's a better way? We get explicit. Instead of one ambiguous, confusing interface, we define two separate, crystal clear ones, one for circle and one for square. Now, in the circle interface, radius is a required property. And in the square interface, side length is required. There's no more ambiguity, no more maybes. Building one of these is a super simple three-step recipe. Step 1, define those unique interfaces for each possibility, like our circle and square. Step 2, and this is the secret sauce, give them a common property with a unique literal type. So the type isn't just string, it's the literal string circle. This kind property is our discriminant. And finally, step 3, just combine them into a single union type. And here it is, the beautiful payoff. When we use a switch statement on that shape.kind property, TypeScript understands everything perfectly. Inside the circle case, it knows that shape must be of type circle, and it gives us full, safe access to the radius property with 0 errors. The code is clean, it's safe, and it's self-documenting. No more guessing and no more using that exclamation point to tell TypeScript, trust me. We have one final, master-level technique to add to our toolkit. Think of this as a safety net for your code, ensuring you never miss a clue, even as your app grows and changes over time. And we're going to build this safety net using TypeScript's special never type.
This is called exhaustiveness checking. So in our switch statement, after handling all the known cases like circle and square, we add a default case. Inside, we try to assign our shape variable to a new variable that's typed as never. Now, the never type literally means this state is impossible and should never happen. If we've actually handled all possible shapes, this code is fine, because that default case should be unreachable.
Now watch the magic. It's like an alarm system for your code. Let's say months from now, a new developer on your team adds triangle to our shape union type. Instantly, our getArea function gets a compile error. Why? Because in that switch statement, if the shape is a triangle, it's going to fall through to the default case. And there, TypeScript tries to assign a triangle to never, which is impossible. The compiler is now our safety net, forcing us to handle the new triangle case. This prevents countless bugs down the road.
So there you have it. We've gone from investigating mysterious errors to proactively designing bug-proof code. From simple typeof guards to the elegant power of discriminated unions and exhaustiveness checking, you now have a full detective's toolkit for mastering type narrowing. So the final question is, how are you going to use these patterns to prevent future mysteries in your own code?
And that's a wrap on our investigation. If you found this deep dive into TypeScript narrowing helpful, show your support with a like, and be sure to subscribe to BuildBytesDaily for more explainers that help you write better, safer code. Thanks for watching, and happy coding!